Transporting heavy equipment for large-scale construction, industrial, and infrastructural projects is one of the most critical and logistically challenging tasks in the world. From offshore wind farms to petrochemical plants, large bridges, and skyscrapers, these projects demand the movement of components that often weigh hundreds or even thousands of tons. To accomplish this, two primary pieces of equipment are essential: self-propelled modular transporters, SPMTs, and supercranes. These machines have revolutionized the transportation and installation of massive components, allowing for the realization of projects that were once deemed impossible due to the sheer scale of their requirements. The role of SPMTs in heavy equipment transport. Self-propelled modular transporters, SPMTs, are specialized vehicles designed to move massive loads with extreme precision. Their modularity and self-propelled nature make them indispensable for industries that regularly deal with oversized and overweight components, such as construction, oil and gas, shipbuilding, and renewable energy sectors. An SPMT consists of multiple axle lines, each capable of moving independently due to advanced hydraulic systems. This feature allows for precise control, enabling the transporter to maneuver in tight spaces and challenging terrains. Each axle line can support and move loads up to 30 tons, and multiple modules can be connected to accommodate the heaviest loads, such as large turbines, offshore platforms, and industrial vessels. The modularity and scalability of SPMTs. One of the defining features of SPMTs is their modularity. This means that individual transport modules can be linked together to carry loads of various sizes and shapes. This flexibility is essential for transporting large and irregularly shaped objects, which are common in heavy industry. Each SPMT module consists of several axle lines, with hydraulic lifting systems that allow them to adjust the height of the transported load. This system also provides leveling capabilities, ensuring that the load remains stable even when traversing uneven terrain. In cases where the load is too large for a single SPMT, multiple units can be synchronized to operate together, creating a system capable of transporting even the heaviest loads across long distances. The precision of SPMT movement. SPMTs are also known for their incredible precision. Due to the advanced hydraulic and control systems that drive each axle, SPMTs can be maneuvered with millimeter accuracy, which is essential when transporting massive and sensitive equipment. In particular, industrial components such as nuclear reactor vessels or offshore drilling rigs require exact placement to ensure the safety and efficiency of operations. The precision and flexibility of SPMTs make them ideal for moving equipment in confined spaces or complex construction sites. This level of control is especially important in projects like bridge installations, where large components need to be transported over uneven or unfinished ground. Supercranes. Lifting the heaviest loads. Supercranes, often referred to as megacranes or heavy lift cranes, are colossal machines designed to lift and position extremely heavy and oversized objects. These cranes are used in various sectors, including infrastructure development, energy, and maritime industries. Capable of lifting loads that can exceed 5,000 tons, supercranes are essential for projects where large, heavy components need to be lifted and installed at significant heights or in challenging environments. Supercranes come in various types, including mobile, tower, and crawler cranes. Each type has specific advantages depending on the nature of the project. Mobile supercranes are highly versatile, capable of being transported to different job sites, while tower cranes provide the height and stability needed for lifting in skyscraper construction and other vertical projects. Crawler cranes, on the other hand, are suited for heavy loads in rough terrains due to their tracks, which distribute the weight of the crane and the load. Key features of supercranes. Supercranes are characterized by their large booms, high lifting capacities, and specialized lifting attachments. The booms of supercranes can reach heights of over 100 meters, and when combined with jib extensions, they can handle loads at great distances. This makes supercranes ideal for assembling tall structures, such as wind turbines or bridge sections. The lifting capacity of supercranes is enhanced by their counterweights, which stabilize the crane and allow it to lift extraordinarily heavy loads. These counterweights can weigh hundreds of tons, and are essential for balancing the crane when it is lifting near its maximum capacity. Moreover, the load-bearing components, such as cables and winches, are made of ultra-strong materials that ensure safety and reliability. In some cases, supercranes can be equipped with custom lifting attachments that are tailored to the specific needs of the project. These attachments can accommodate unusual or oversized loads, ensuring that the crane can safely and efficiently lift and place components in the desired locations. Applications of supercranes. Supercranes are used in a wide range of projects, from industrial installations to infrastructure development. One of the most common uses is in the construction of power plants, where large equipment such as boilers, reactors, and turbines need to be lifted and installed. These components often weigh several hundred tons, and supercranes are the only machines capable of handling such massive loads. Another major application of supercranes is in the oil and gas industry, particularly in the construction of offshore platforms. These platforms are assembled from large modules that need to be lifted into place, often in challenging marine environments. Supercranes provide the lifting power and precision necessary for these operations, ensuring that the components are installed safely and efficiently. The importance of SPMTs and supercranes in megaprojects. 1. Facilitating large-scale construction projects. Megaprojects, such as bridge construction, skyscraper development, and large industrial complexes, rely heavily on the use of SPMTs and supercranes. These machines are essential for moving and installing the massive components that make up these structures. For example, in the construction of the world's largest bridges, such as the Millau Viaduct in France or the Akashi Kaikyo Bridge in Japan, enormous steel and concrete sections need to be transported and lifted into place with extreme precision. SPMTs are used to transport these sections from the fabrication site to the installation site, while supercranes are employed to lift them into position. Without the capabilities provided by SPMTs and supercranes, many of these projects would be logistically impossible. These machines enable the transportation and lifting of components that are simply too heavy or large for conventional methods. By reducing the need for disassembly and reassembly, they also help to reduce construction times, which is a critical factor in the success of large-scale projects. Two. Increasing efficiency and safety. SPMTs and supercranes also play a critical role in improving the efficiency and safety of heavy equipment, transport, and installation. In the past, moving large components often required complex and time-consuming operations involving multiple vehicles and lifting devices. Today, SPMTs and supercranes streamline this process by providing an all-in-one solution for both transportation and lifting. The precision of SPMTs ensures that loads can be moved with minimal risk of damage, even when navigating through tight spaces or difficult terrains. This reduces the likelihood of accidents and helps to prevent costly delays. Likewise, the lifting capabilities of supercranes allow for the safe and efficient installation of heavy components at significant heights. These cranes are designed with multiple safety features, such as load monitoring systems and automated control mechanisms, that help to ensure safe operations even under challenging conditions. Three. Supporting the growth of renewable energy. One of the key areas where SPMTs and supercranes are making a significant impact is in the renewable energy sector, particularly in the construction of wind farms. Offshore wind turbines, in particular, are incredibly large and heavy, with some models exceeding 100 meters in height and weighing several hundred tons. Transporting and installing these turbines requires both the precision of SPMTs and the lifting power of supercranes. SPMTs are used to transport the turbine components, such as the blades and the nacelle, which houses the generator, from the manufacturing site to the installation site. Supercranes are then employed to lift these components into place, often in challenging offshore environments. The use of these machines has helped to reduce the cost and time required to build wind farms, making renewable energy projects more economically viable. 4. Enabling the development of large industrial facilities. In the industrial sector, SPMTs and supercranes are critical for the construction of large facilities, such as oil refineries, chemical plants, and power stations. These facilities require the transportation and installation of massive equipment, including reactors, distillation columns, and cooling towers. SPMTs are used to move these components from the manufacturing site to the construction site, while supercranes are employed to lift them into place. In some cases, entire modules of a facility are assembled off-site and then transported to the installation site using SPMTs. This modular construction approach helps to reduce the time and cost of building large industrial facilities, as it allows for parallel construction activities. Once the modules are transported to the site, supercranes are used to lift and position them, ensuring that the facility is assembled quickly and efficiently. Case studies. SPMTs and supercranes in action. 1. The Burj Khalifa, Dubai. The construction of the Burj Khalifa, the tallest building in the world, required the use of supercranes and SPMTs to transport and install the massive steel and concrete sections that make up the tower's structure. The cranes, with their ability to lift heavy loads to great heights, were essential for the assembly of the upper levels of the building. Meanwhile, SPMTs were used to transport large sections of the building's facade and structural components from the fabrication site to the construction site. Two. The Queensferry Crossing, Scotland. The Queensferry Crossing, a major bridge project in Scotland, involved the transportation and installation of large bridge sections using SPMTs and supercranes. The bridge's central tower sections, each weighing over 800 tons, were transported to the construction site using SPMTs and then lifted into place using supercranes. This project highlighted the importance of these machines in enabling the construction of large infrastructure projects. Three. Offshore oil platforms. Gulf of Mexico. In the Gulf of Mexico, the construction of offshore oil platforms relies heavily on the use of SPMTs and supercranes. These platforms are assembled from large modules that need to be transported to the installation site and lifted into place. SPMTs are used to move the modules from the fabrication yard to the dock, where they are loaded onto ships. Once at the installation site, supercranes are used to lift the modules onto the platform structure. Let's talk a little about the history of the SPMT machine and supercrane. The self-propelled modular transporter, SPMT, and supercranes have become indispensable in the construction, heavy industry, and transport sectors. These machines are marvels of modern engineering, designed to transport and lift massive loads that would otherwise be impossible to move. However, their development was not an overnight achievement. The history of SPMTs and supercranes reflects a combination of technical innovation, problem-solving, and adaptation to the evolving needs of industries handling increasingly large and complex projects. In this essay, we will explore the origins, evolution, and significance of SPMTs and supercranes, tracing their historical journey and highlighting the key milestones in their development. The genesis of heavy transport and lifting technologies. Before the invention of modern SPMTs and supercranes, the transportation and lifting of large loads were handled using rudimentary means. Early civilizations employed basic mechanical tools like pulleys, levers, and wheeled carts for lifting and moving objects. The construction of ancient structures such as the pyramids of Egypt or Stonehenge relied on these principles, combined with significant human labor. Though effective for their time, these methods had limitations when it came to transporting extremely heavy or oversized loads over long distances or uneven terrain. By the late 19th century, the Industrial Revolution had spurred the development of more advanced transport and lifting mechanisms, including steam-powered cranes and rail systems. The need to move large machinery, industrial equipment, and building materials gave rise to the first specialized cranes designed for heavy lifting. The expansion of railways also contributed to the movement of large goods. However, these early machines still lacked the flexibility and precision needed for handling ultra-heavy, oversized loads. The early development of modular transporters. The direct precursor to the modern SPMT can be traced back to the development of modular transporters in the mid-20th century. During this period, the growth of heavy industries such as oil and gas, shipbuilding, and civil construction created a need for more efficient methods of transporting large equipment, prefabricated structures, and industrial modules. In the 1950s and 1960s, engineers began experimenting with modular transport systems to meet these demands. The goal was to create vehicles that could be assembled in various configurations to accommodate different load sizes and weights. Early modular transporters used conventional wheeled platforms, combined with hydraulic systems for lifting and stabilizing loads. These systems were often towed by trucks or powered by external means, limiting their flexibility. A major breakthrough came in the 1970s, when transport companies sought more versatile, self-powered solutions. The development of hydraulic-driven systems allowed transporters to become more independent and capable of precise movement. This innovation led to the creation of multi-wheeled transporters, capable of moving exceptionally heavy and large objects across industrial sites and infrastructure projects. The birth of the self-propelled modular transporter, SPMT. The term self-propelled modular transporter, SPMT, first emerged in the late 1970s and early 1980s, when modular transporter technology was enhanced with self-propulsion capabilities. One of the key innovators in this field was Scheuerle Fahrzeugfabrik, a German manufacturer specializing in heavy-duty transport equipment. Scheuerle developed the first self-propelled transporter, which combined hydraulic suspension systems with multi-axle platforms. This development allowed for greater maneuverability and load control, as the transporter could now be steered and propelled without external towing vehicles. The SPMT revolutionized the transport industry by offering a level of flexibility and efficiency that had previously been unattainable. Its hydraulic suspension system allowed it to handle uneven terrain, while its modularity enabled it to be configured in different formations based on the size and shape of the load. Additionally, the self-propulsion feature gave operators the ability to move large objects with incredible precision, even in tight or constrained spaces. As the technology advanced, companies like Goldhofer, Mamoe, and Cerence began to adopt and further develop SPMTs, contributing to their widespread use in the 1980s and 1990s. These companies played pivotal roles in refining the design, expanding the capacity, and incorporating remote-controlled systems that enabled even more precise operations. The rise of SPMTs in megaprojects. SPMTs gained global recognition for their role in some of the largest and most complex engineering projects of the late 20th and early 21st centuries. Their ability to transport oversized loads made them indispensable in industries such as oil and gas, power generation, shipbuilding, and infrastructure development. The modular nature of the SPMT made it possible to combine multiple units to carry loads weighing thousands of tons, which was particularly useful in projects involving the installation of large industrial equipment, prefabricated structures, and bridge sections. One of the most notable early uses of SPMTs was during the construction of offshore oil platforms. These platforms, which can weigh tens of thousands of tons, are often assembled onshore and then transported to the installation site using a combination of SPMTs and ocean-going vessels. The precision and stability offered by SPMTs were critical in ensuring the safe transport and installation of these massive structures in harsh marine environments. Another significant application of SPMTs was in the transportation of large bridge sections. For example, the Millau Viaduct in France, completed in 2004, used SPMTs to transport and position large segments of the bridge deck. The viaduct, which is one of the tallest bridges in the world, required exceptional precision during the construction process, and SPMTs played a key role in making this possible. The use of SPMTs in power generation projects, particularly in the construction of nuclear power plants, also demonstrated their importance. Nuclear reactors, steam generators, and other large components need to be transported and installed with utmost care, as any damage could have severe consequences. SPMTs allowed for the safe and efficient handling of these sensitive components, contributing to the success of numerous power plant construction projects worldwide. The evolution of supercranes. While SPMTs were revolutionizing heavy transport, another parallel development was taking place in the realm of heavy lifting: the evolution of supercranes. The history of cranes dates back thousands of years, with the first simple cranes being used by the ancient Greeks for construction. These early cranes were powered by human or animal labor and had limited lifting capacities. Over time, advancements in engineering led to the development of steam-powered and, later, diesel and electric-powered cranes. The 20th century saw significant advancements in crane technology, with the introduction of mobile cranes, tower cranes, and crawler cranes. However, as industrial projects grew in scale and complexity, it became clear that a new class of cranes would be needed. Cranes capable of lifting extraordinarily heavy loads, often exceeding 1,000 tons. This need gave rise to the development of supercranes in the late 20th century. Supercranes are defined by their ability to lift exceptionally heavy loads, sometimes as much as 5,000 tons or more. These cranes come in various forms, including mobile cranes, tower cranes, and crawler cranes, each with specific applications. The development of supercranes was driven by the need for higher lifting capacities in industries such as oil and gas, power generation, shipbuilding, and infrastructure development. The development of the first supercranes. The first supercranes began to appear in the 1970s and 1980s, coinciding with the rise of large-scale industrial and infrastructure projects. One of the early pioneers in this field was Liebherr, a German company that had already established itself as a leader in crane manufacturing. Liebherr introduced several high-capacity cranes, including the LR 13000, a crawler crane capable of lifting up to 3,000 tons. This crane was specifically designed for projects involving the assembly of large industrial structures, such as offshore oil platforms and power plants. Another key player in the development of supercranes was Mammoet, a Dutch heavy lift and transport company. Mammoet's fleet of supercranes, including the PTC 200DS and the MTC 15, became widely known for their ability to handle ultra-heavy loads in challenging environments. These cranes were used in some of the world's most complex projects, including the construction of petrochemical plants and the installation of large bridge sections. Sarens, a Belgian company specializing in heavy lifting and engineering, also played a significant role in the development of supercranes. Sarens introduced several innovative cranes capable of lifting and transporting massive loads, including the SCC 16000 and SGC 120. These cranes were employed in a variety of mega projects, from offshore wind farm installations to the construction of large industrial facilities. Super cranes in modern megaprojects. As industrial projects grew in size and complexity, super cranes became an essential tool for handling the lifting requirements of these megaprojects. One of the most notable examples is the use of super cranes in the construction of offshore wind farms. Offshore wind turbines are massive structures, with blades exceeding 100 meters in length and nacelles weighing several hundred tons. Installing these components in offshore environments requires cranes with both high lifting capacities and precise control. Super cranes have also been instrumental in the construction of large bridges, such as the Akashi Kaikyo Bridge in Japan, the longest suspension bridge in the world. The bridge's construction involved the lifting and installation of large sections of the bridge deck, which required the use of super cranes with high lifting capacities and exceptional stability. In the oil and gas industry, super cranes have been used to assemble offshore platforms, refineries, and other large structures. These projects often involve the lifting of prefabricated modules that weigh thousands of tons. Super cranes provide the lifting power needed to handle these massive loads, while their advanced control systems ensure that the components are installed safely and accurately. The synergy between SPMTs and super cranes. One of the most significant developments in the history of heavy transport and lifting has been the synergy between SPMTs and super cranes. These two technologies complement each other, enabling the transportation and installation of massive loads that would otherwise be impossible to handle. In many mega projects, SPMTs are used to transport large components to the installation site, while super cranes are used to lift and position them. For example, in the construction of offshore oil platforms, SPMTs are used to transport prefabricated modules from the fabrication yard to the dock, where they are loaded onto vessels. Once the modules arrive at the installation site, super cranes are used to lift them into place on the platform structure. This combination of transport and lifting technologies has allowed industries to take on larger and more complex projects, reducing construction times and improving efficiency. The use of SPMTs and super cranes has also improved safety, as these machines are designed to handle heavy loads with precision and stability, minimizing the risk of accidents. Conclusion: the legacy and future of SPMTs and super cranes. The history of SPMTs and super cranes is a testament to the ingenuity and innovation of engineers and manufacturers who recognize the need for specialized equipment to handle the challenges of modern megaprojects. From their humble beginnings as basic mechanical tools, these machines have evolved into highly sophisticated and essential components of the global construction, industrial, and energy sectors. SPMTs have revolutionized the way heavy loads are transported, offering unparalleled flexibility, precision, and efficiency. Meanwhile, super cranes have redefined the limits of heavy lifting, making it possible to assemble and install some of the largest structures ever built. Together, these machines have enabled the construction of massive industrial complexes, offshore platforms, bridges, and skyscrapers that shape the modern world. As technology continues to advance, we can expect further innovations in SPMT and super crane design. Automation, improved materials, and enhanced control systems will likely increase the capabilities of these machines, making them even more integral to the success of future megaprojects. The legacy of SPMTs and super cranes will continue to evolve, shaping the infrastructure and industrial landscape for generations to come.